Swayam Prabha. Digital India. Educated India.
In the last lecture, we were discussing the effective conductivity of a composite material which consists of spherical particles embedded in a matrix. This we had taken up as an illustration of the solution of the diffusion equation, diffusion dominated transport in a spherical coordinate system. And I was using this to illustrate for you how we can do the separation of variables procedure in a spherical coordinate system for this particular problem. So, we had spheres of particles, spherical particles of radius r in a matrix in which there was an imposed temperature gradient in the z direction. Okay. This imposed temperature gradient, if there were no particles, the flux would just be equal to the matrix conductivity times the temperature gradient. However, since we do have particles here, the conductivity is going to be different from just the matrix conductivity, because the presence of the particles distorts the heat flux lines. If the particles were not present, the flux would just be along the z direction. However, since there are particles present, there is going to be a distortion of the flux. If, as I showed you in the previous lecture, if the matrix particles had a higher conductivity, the flux lines would come in towards the particles, whereas if it had a lower conductivity, it would go out. Okay. We had written the average flux as a volume average of the flux over the entire volume, okay, which basically includes the matrix and the particles. So, we have to take the flux over the matrix and the flux over the particles. Over the matrix, we know that the matrix conductivity is just equal to Km, whereas the particle conductivity is equal to Kp. That has to be multiplied by the individual temperature gradients within the matrix and within the particle in the z direction. I had rewritten this as two contributions, one over the entire volume of the matrix conductivity times the temperature gradient, the other over the particles alone of the difference in conductivity between particles and matrix times the temperature gradient. This makes sense because the matrix part is what would have been there if there were no particles present, and the particle part is the additional contribution, either positive if the particles are more conductive or negative if the particles are less conducting in comparison to the matrix. The matrix part, of course, is the volume average over the entire volume, of course, gives me back the temperature gradient that was imposed, because the volume average of the temperature gradient has to be equal to the imposed temperature gradient. And then I was reduced to finding out the integral over the particles of the change in conductivity times the temperature gradient within the particle, okay, the difference between the particle and the matrix conductivities. Since we were considering the non-interacting limit, where the temperature around one particle is not affected by all the other particles, I wrote this as the total number of particles times the integral over one particle of the temperature gradient in the z direction in that particle. And this final term is what we were trying to evaluate in a spherical coordinate system in the previous lecture. Okay. So, we had to solve the conservation equation in a spherical coordinate system with the boundary condition that the temperature far from the particles is a linear gradient in the z direction. At the particle surface, the temperatures are equal in both the particles and the matrix, and the fluxes perpendicular to the surface are equal, because what leaves the particles has to invariably go into the matrix. I had outlined for you the separation of variables procedure for solving this problem. Okay. You separate variables into a function of the radius times a function of theta, theta in a spherical coordinate system goes from 0 along the plus z axis to pi along the minus z axis. Okay. For the theta coordinate alone, okay, after doing the separation of variables, we got an equation in which there were two terms. One is only a function of r and the other is only a function of theta. Both have to be constants. In the theta direction, okay, we get an equation which is in the form of a Legendre equation. Okay. This equation has finite solutions at the coordinate boundaries at theta is equal to 0 and theta is equal to pi. Okay, it has finite solutions at those coordinate boundaries only if this constant, okay, is equal to minus n into n plus 1, where n is an integer. Okay. You can show that, that I will not go through because it is a subject in applied mathematics, but you can show analytically by a series solution that these solutions exist only if n is an integer. And the solutions are of the form Pn0 of cos theta. The superscript 0 I will come to a little later. Okay. I wrote down for you the first few of these, okay, P0, P1, P2, etc. Okay. These are all polynomials. Pn is a polynomial of order n. P0 is just 1. P1 is equal to x itself or cos theta itself. P2 is 3 cos square theta minus 1 by 2 and so on. Okay. And these satisfy the orthogonality relations that if you multiply any two of these and integrate over the domain in x from minus 1 to 1, you get a non-zero value only when n is equal to m. Okay. So, that was a solution in the theta direction. This direction by default was the homogeneous direction, because even though there was no physical boundary, there are coordinate boundaries, and along those coordinate boundaries you require that the solution has to be finite. So, that is the homogeneous direction in this case. Alternatively, the derivative of the solution with respect to theta has to be 0. Okay. We solved in the other direction, in the r direction, because we know from the theta equation that this constant is n into n plus 1. So, we put that in the r direction, and we got the solution as power laws. Okay. So, the total temperature field was equal to A n times r power n plus B n by r power n plus 1 P n 0 of cos theta. Now, the solution for the temperature field is actually 0. So, that was the solution that I had got. What are the boundary conditions? Okay. Boundary conditions. Okay. First one is that as r goes to infinity, okay, t is equal to t prime, okay, z, which is t prime r cos theta. And since I told you that I had written down, I should make a slight correction here. Okay. Okay. I should write this as P0 0, P1 0 and P2 0 in this case. Okay. I told you that P0 0 of cos theta is equal to 1, P1 0 of cos theta, P1 0 of x was x itself. So, P1 0 of cos theta was cos theta, okay. P2 0 of cos theta is equal to 3 cos square theta minus 1 by 2. Okay, and so on. Okay. So, therefore, I can write this equivalently as T prime r into P1 of cos theta, okay, because we know that P1 of cos theta is equal to cos theta. Okay. P2 and P3 and so on. Okay. You can extend this series by solving that equation by a series solution. Okay. Okay. So, therefore, as r goes to infinity, the driving term, the inhomogeneous term is of the form P1 of cos theta. Okay. Okay. Then at r is equal to r, okay, you have T matrix is equal to T particle. Okay. T matrix is equal to T particle and K matrix times partial T matrix by partial r is equal to K particle times partial T particle by partial r. Okay. And the solution is of this form. Okay. So, now I can separate out the solution into different components for n is equal to 0, n is equal to 1, n is equal to 2, etc., and solve using boundary conditions for each one of them. Okay. Solve using boundary conditions for each one of them. Okay. If you look at the solutions for n is equal to 0, n is equal to 1 and so on. Okay. So, let us take first for n is equal to 0. I have A0 plus B0 by r, okay, into P00 of cos theta, okay, is the solution. Okay. As r goes to infinity, right, the temperature, okay, T is equal to T prime r P1, okay, T prime r times P10. Okay. So, if actually were to calculate the boundary condition for P0, okay, that would be 0, because this forcing at infinity is of the form P1. Okay. If P1 and P0 are orthogonal to each other. Okay. So, therefore, the forcing in the P1 Legendre polynomial does not result in any contribution to the 0 Legendre polynomial, because these are orthogonal polynomials. Okay. The forcing has to be equal to 0, therefore, for P0, okay, far from the surface. Okay. And then I have the boundary conditions that, okay, Tm is equal to Tp, okay, and Km partial Tm by partial r is equal to Kp partial Tp by partial r. Okay. These boundary conditions are effectively, they are homogeneous, there is no forcing in these boundaries. It just states that the temperature on both sides is equal and the flux on both sides is equal. Okay. The disturbance to the temperature field, which results in a non-zero temperature around the particle, comes from the forcing far from the surface. Okay. That forcing is of the form P1 of cos theta. Okay. That forcing does not appear in the equation at n is equal to 0. Okay. Since the forcing does not appear in the equation at n is equal to 0, if the temperature for n is equal to 0 is identically equal to 0, okay, it satisfies all the boundary conditions, okay, because there is no forcing as r goes to infinity, and 0 temperature actually satisfies these two conditions. Okay. If I assume n is equal to 0, okay, for the first term in the expansion. As I said, all of these Legendre polynomials are all orthogonal to each other. Okay. So, therefore, I can always decompose these, okay, for n is equal to 0, n is equal to 1, n is equal to 2 and so on. Decompose the boundary conditions also for n is equal to 0, n is equal to 1, n is equal to 2 and so on. Solve each of those individually, okay, and then add them up to get the solutions. Okay. Because each one of these is orthogonal. If I multiply one solution by a Legendre polynomial of some other order and then integrate, I will get 0 as the result. Okay. So, for n is equal to 0, okay, since the forcing is 0 as r goes to infinity, and these boundary conditions just relate the temperature and the flux at the surface. If the temperature were 0, all of these conditions would be satisfied. This is a linear equation, therefore, there should be only one solution, and that solution is the 0 solution, because there is no forcing in the equation at n is equal to 0. Let us take n is equal to 1. Okay. The solution is of the form A1 r plus B1 by r square, P1 0 of cos theta. Okay. This is the solution in both the matrix and the particle. Okay. The constants will be different, of course, in the particle and matrix, but the solution will be of this form. Okay. As r goes to infinity, I have t is equal to t prime r P1 of cos theta. Okay. And then I have Tm is equal to Tp, okay, Km partial Tm by partial r is equal to Kp partial Tp by partial r. Okay. Now, this has a non-trivial solution, because I have a non-trivial forcing in the P1 Legendre polynomial. Okay. I have a non-trivial forcing in the P1 Legendre polynomial. Therefore, this will have a non-trivial solution. Okay. I cannot just use temperature is equal to 0 as the solution, because it does not satisfy this boundary condition in the limit as r goes to infinity. Okay. Similarly, if I were to do it for n is equal to 2, for example, and so on, I will get A2 r square plus B2 by r cubed, okay, P2 0 of cos theta. Okay. For this, once again, the forcing is 0, because the forcing is of the form P1 of cos theta, okay, which is orthogonal to P2. Okay. So, as far as the P2 symmetry is concerned, the forcing is 0. Okay. Okay. So, basically I have t is equal to 0 as r goes to infinity. Then I have the homogeneous boundary conditions, Tm is equal to Tp at r is equal to r. Okay. 0 temperature satisfies all of these conditions as well, and so on for all other orders n. Okay. So, since the forcing has the symmetry P1 0 of cos theta, the forcing has the symmetry P1 0 of cos theta, it projects only onto the P1 Legendre polynomial solution. It projects onto the solution only for n is equal to 1. Okay. All of these harmonics are all orthogonal to each other. This forcing projects only onto the solution at n is equal to 1. For n is equal to 0, 2, 3, etc., this forcing is equal to 0. Okay. Therefore, for 0, 2, 3, etc., I have a forcing that is 0, I have boundary conditions which basically relate the temperature in the matrix and the particle and the flux in the matrix and particle. If the forcing is 0, all of these conditions are satisfied if the temperature, or rather A0 and B0 here, if both of them are 0, all of these conditions are satisfied. Similarly, if A2 and B2 are 0, all of these conditions are satisfied. That is because there is no forcing with symmetry of P0, P2, etc. Okay. The only forcing is with symmetry P1, and since all of these Legendre polynomials are all orthogonal to each other, the solution should also have the same symmetry. Okay. The solution should also have the same symmetry. So, just based upon symmetries alone, we have made the argument that only the term with n is equal to 1 has to be included in the solution, okay, because there is no forcing with symmetry of P0, P2, etc. All of these are all orthogonal to each other. Therefore, if the forcing is has symmetry P1, all of the solutions also should have the same symmetry P1. Okay. There is no forcing in the symmetry P2, P0, P2, etc., because if I take the boundary condition and expand it out in a Legendre polynomial expansion, the only term that will be non-zero is the one corresponding to P1. The terms corresponding, because they are all orthogonal, the terms corresponding to P0, P2, etc. will all be 0. Okay. Therefore, the solutions for the temperature with n is equal to 0, 2, etc. will all be 0. And that just comes out of the orthogonality of the Legendre polynomials. Okay. What that means is that the temperature in the particle has got to be equal to A particle times R plus B particle by R square, P10 of cos theta for n is equal to 1. Okay. And the matrix temperature has to be equal to A matrix times R plus B matrix by R square. Okay. Now, the boundary condition, okay, as R goes to infinity, the temperature in the matrix is equal to T prime R cos theta. Okay. As R goes to infinity, you can see that this term goes to 0. Okay. As R goes to infinity, 1 over R square goes to 0, and what that would imply is that A m is just equal to T prime. Okay. That satisfies the boundary condition as R goes to infinity. Okay. So, therefore, the matrix temperature is equal to note that P1 of cos theta is just cos theta itself. Okay. As far as the particle is concerned, you require that at R is equal to 0, temperature has to be finite. Okay. At R is equal to 0, the temperature has to be finite, which means that this coefficient Bp has to be equal to 0. Which means that this coefficient Bp has to be equal to 0. Because you have Bp by R square, and if Bp were non-zero, then the temperature would go to infinity. Okay. Therefore, the temperature in the particle is just equal to A particle R times cos theta. And then now you have the boundary conditions at the particle surface. Okay. At R is equal to R, Tp is equal to Tm, which implies that Ap, okay, into R is equal to T prime R plus Pm by R square. Okay, just equating the temperatures at the surface. Okay. Also, at R is equal to R, the fluxes have to be equal. Okay. What this implies is that Ap, okay, is equal to T prime. When I take the derivative of this term with respect to R, okay, I will get minus 2 Bm by R cubed. Okay. So, you can solve these two equations to find what is Ap and Bm, okay, to get the solutions for Ap and Bm. Okay. The solutions are quite straightforward, you just have to solve these two simultaneously. Okay. And what you will get is that Ap is equal to 3 T prime by 2 plus Kr, okay, and Bm is equal to 1 minus Kr T prime by 2 plus Kr into, I think it is R cube. Okay. Where Kr is equal to the ratio of the conductivities. Okay. You can solve this quite easily. Okay. And with this, the temperatures in the particle becomes Tp is equal to 3 T prime r cos theta by 2 plus Kr, okay. And the matrix temperature is equal to T prime r cos theta plus 1 minus Kr, okay, T prime by 2 plus Kr, okay, into r cube by r square into cos theta. Okay. So, this has given us the temperatures in the matrix and in the particle. Okay. This has given us the temperatures in the matrix and the particle. In particular, the particle temperature actually is only a function of z. Okay. The particle temperature, as I have written it here, is only a function of z. I can rewrite in terms of z, 3 T prime z by 2 plus Kr. Okay, so, that is the temperature within the particle. Now, we have to determine the effective thermal conductivity. Okay, so, let us go back and get us the expression for the effective thermal conductivity. Okay. This is the expression for the average flux. Okay, this is the expression for the average flux, okay, and we had written it in this form. Okay, we had written it in this form. Okay. Okay. So, this is equal to minus Km T prime minus, okay, Kp minus Km, okay, n by V. Okay. Let me write it here. Okay. Integral over the particle of partial t by partial z, okay, within the particle. Okay. Integral over the particle of partial t by partial z over the particle. Okay. And now we have the temperature within the particle. Okay. Temperature is equal to 3 T prime, okay, z by 2 plus Kr. Okay. We just calculated that from the spherical harmonic expansion, which means that the temperature gradient within the particle is going to be equal to 3 T prime by 2 plus Kr. Okay. So, this is a constant. This temperature gradient within the particle is a constant. Okay. This temperature gradient within the particle is a constant. Therefore, this is minus Km T prime minus of Kp minus Km. Okay. Number of particles, the volume of one particle divided by the total volume, okay, times partial t by partial z, which is 3 T prime, okay, divided by 2 plus Kr. Okay. So, this is the expression for the average flux, okay, within the particle. Okay. Now, if I take divided by Km, okay, or alternatively I can write this as minus Km T prime into 1 plus, okay. I take the Km and T prime outside, okay, and I will get here Kp minus Km by Km, okay, into n Vp by the total volume, okay, into 3 by 2 plus Kr. Recall that Kr was the ratio of the thermal conductivities of the particle and the matrix. Okay. So, I can write this as minus Km T prime into 1 plus 3 Kr minus 1 by 2 plus Kr into n times the volume of the particles divided by total volume. N is number of particles, V is volume of one particle, and the V in the denominator is the total volume. Okay. So, it is basically the ratio of the volume occupied by the particles to the total volume. Okay. The ratio of the volume occupied by the particles to the total volume, that is what is called the volume fraction. Okay. That is what is called the volume fraction phi. Okay. So, this gives me the effective thermal conductivity of a composite. Okay. The effective thermal conductivity is effectively the matrix thermal conductivity times this additional factor due to the presence of the particles. Okay. So, K effective is effectively K matrix times 1 plus 3 into Kr minus 1 by 2 plus Kr into the volume fraction of the particles, where Kr is equal to the particle conductivity divided by the matrix conductivity. That is the relative conductivity of the particles with respect to the matrix. Okay. So, that is the final solution for the effective thermal conductivity of a composite. Okay. If Kr is greater than 1, the effective conductivity is greater than the matrix conductivity. If Kr is less than 1, the effective conductivity is less than the matrix conductivity, as we had expected. It is important to note that this effective conductivity depends only upon the volume fraction of the particles. It does not depend on either the number of particles or the volume of each particle, regardless of whether you have a larger number of small particles or a smaller number of large particles. If the volume fraction is the same, the effective thermal conductivity will be exactly the same. Okay. So, this completes our analysis of the effective thermal conductivity of a composite material in the dilute limit, where the temperature field around one particle is not affected by the presence of the other particles. I have shown you how to use separation of variables to obtain a solution for the temperature field around a spherical particle, and use that in order to calculate the effective flux. This we did for an axisymmetric system, because it was symmetric about the z axis. There was no phi dependence in this expansion. Okay. In general cases, you will have a phi dependence. Okay. In that case, how does one solve the problem? That I will continue in the next lecture. Okay. I will briefly go through how this problem was solved and then show you how to solve it for the more general case. We will continue this in the next lecture. I will see you then.